So how do power meters work? Part 4 of 10. Here we're going to talk about the voltage divider. We're talking about the shunt in the last one. Combining these two is going to be extremely powerful. So let's get through what a voltage divider is. It's a series of resistors used so that the voltage of one resistor is a fraction of the total resistance. Okay, so if I had two resistors here in this circuit, R1 and R2, and if R1 was 10 times bigger than R2, right? Then this one down here is 1 ohm, and this one is 10 ohms. Well, then this would be the total resistance as seen by the load appears to look like 11 ohms. So the voltage drop of this resistor would be 10 ohms divided by 11 ohms. The ohms cancel out, and so this becomes a fraction of 10 over 11 times your voltage of the source. And so that would be the voltage drop of that resistor. And the voltage drop of this bottom resistor would be 1/11 times Vs. Okay. And so that's how you're supposed to, use voltage dividers. And we use them, in power meters and voltage meters so that we can reduce the voltage going to our actual metering device and lower, so we don't want to apply 480 to a tiny little meter, right? We might want to apply 4.8 volts or 5 volts, and so we can scale it down, and this is a way to scale it down. When you're building voltage dividers, and if you want some help with it, pro tip: build and try in a circuit simulator program like iCircuit or there's plenty of other circuit simulator program. So we're going to go into a simulator right now and show what this really looks like. Okay, so here we are inside of a circuit simulator program. This is called iCircuit. And so what we have going on here is we actually have two going on. We have the shunt here on the bottom left right here where I'm circling, and then we have the voltage divider right here. So I'm going to take the voltage divider and just open circuit this so it's not part of what we're looking at. And right now what we're going to talk about is the shunt, okay? So right now, this is just a switch that I put in here so that way you can see what it looks like when we bypass. This 10 ohm resistor is our load. So 10 ohms and 100 volts, we have 10 amps flowing. You can see that on the left over here, okay? If I open the switch, we have nothing flowing. So 10 amps is flowing. Now, if I wanted to pass that 10 ohms, right, or that 10 amps through another resistor, like a shunt that was, 5 milliohms, then I would have an appreciable amount of voltage dropped across that, which is almost 50 millivolts, right? 10 amps times 5 milliohms is going to be almost, if you do the math for this, it's actually, let me get a calculator out. It's actually 10 plus 0.005, and that's the actual resistance of the circuit, which is why we have that 49.98 down there, okay? So if we were to go ahead and do 100 volts divided by 10.005, that's the actual current, but the circuit simulator just rounding up to 10 for us. And then we multiply this again times our 5 milliohms, and that would get us the actual voltage drop, which we should expect it to be this 49.98. And it is, right? So times 1,000. There you go. So 49.98. This is again rounding up. It's 49.975. That's where this comes from, okay? So this is how this works. And if you notice, right, this is the resistance of the shunt. If I change the resistance of the shunt, a couple things happen. One, if I go up too much, what I'm doing now is I'm actually lowering the current going through the load. So what I'm actually doing is, if you look right here, we have a wattage drop going across our shunt now of 81 watts. And that is not something that we want. This thing's going to heat up and start smoking. So we want it to be very low current. Excuse me, high current. It's not impacting the current, but very low voltage, right? So if we can get a low resistance, it will have an appreciable low voltage across it. And therefore the power drop of this thing now is 10 milliwatts, right? and therefore it's no longer pulling power from the load or the source, and all of the power primarily is still going to the load. Okay, that's the important thing about this. If I were to sit here and keep lowering my resistance of my load, in other words, I put more parallel loads or whatever on it, right? I can get up to almost 100, almost 100 amps right here. And so if I were to sit here and change this resistance, right, I could still see now I'm affecting it by at least to almost 2%, right? So that's not the goal. The goal is to minimize the resistance of our shunt. Additionally, along the same lines, I'm going to close this circuit now so that way the shunt is bypassed. We have 100 amps flowing. Also, when we measure voltage, we're going to measure in parallel, right? When we measure this current right here with this shunt, we're going to do it in series. But when we measure this, do this voltage divider, we're going to do it in parallel. So when we apply this in parallel, what we want to do is make sure that we are not pulling power from the source, right? So as you've seen, the power went up just, or the current went up just a little bit. We have milliwatts. Almost, you combine these together, it's 1 watt, right? You can see it's 10.01 kilowatts. So we got 1 watt going to these two combined. All right. If your multimeter, if you hook this up, what you'll notice is that your multimeters, if you read the manual, also that's another way, they're at almost 1 mega ohm resistance, right? And so now look at how much we've pulled from the source. This thing is 9 milliwatts, and this one's 5 microwatts about, right? So that's the important thing here, is to make sure that you are not pulling power from the source. If we just hooked up our little power meter directly to this, well, it could be too much voltage, and then this, the power meter is only 500 ohms, or the little scale meter is, you're going to see it later, the varsal meter is only 500 ohms or 20 ohms or something. And so we'll smoke that little thing, right? So we need to put a series resistor here. And you can see that your voltage right here is in the millivolts, right? Which means that the current running through this thing is in the microamps. Okay, so hopefully this clarifies how we would use a shunt. A shunt is going to be our series current measurement, and our voltage divider is going to be our parallel voltage measurement. And you'll see this a little bit more later.